Hello, everyone. Today is April 5th. I'm recording the lecture for Thursday, April 4th. I'm out of town. So this is going to be lecture 19th. I checked the sound, checked the video. I think everything works. First things first, I have to clean something up. So I noticed last time when we talked about entropy and uh, chemical potential of ideal gas, I wrote something like that. It's the usual Sackur-Tetrode formula. It has inside something like this type of thing. I mean, we've seen it many, many times. And I said, this is V and this is V quantum. I was wrong. So the V quantum is basically just this. This is equal to 1 over V quantum. This can also be written in the temperature form, and then it would be 2 pi mkt h squared to the power 3 halves. And again, this is 1 over V quantum. So when we write it like this, then this would be basically, it has the structure V over V quantum over N. And this then gives rise to mu equals to basically kt log of n V quantum over V. Okay, so now this is proper. So it's this n that I was missing because I attributed the n to be part of V quantum, and I wrote V quantum over V. No, it's n times V quantum over V. And then it would be correct to say that this is log of rho over rho quantum. So this I wrote properly, but I was missing the n. And someone should have caught me and said, wait a second. 1 over V is not rho. It has to be n over V. And the reason is because I erroneously assumed that n is absorbed in the V quantum. No, V quantum is this quantity right here. Okay. Then let's recall what we did. So we talked about grand canonical ensemble. Let's see, let me mark the time. This is this is what, 2:36, 2:30. Ensemble, in other words, well, first of all, before the word ensemble, just we're talking about a system that's able to exchange particles and energy with the bath, and the bath is characterized by, so this is the bath, and it's a particle and energy bath. So, and it's characterized by temperature and chemical potential. Okay, bath is very large, so these quantities are fixed, and the system has a fixed, for example, fixed volume. We'll talk about other systems that are not volume-based, for example, magnets, and then there would be something equivalent to that. Okay, it would be magnetization. Anyway, this situation now where the word ensemble comes in is in talking about probabilities, right? So we talked about what's the ratio of probability that a subsystem is in state I versus state J, and we came up with this type of distribution called, I guess it would be called Gibbs grand canonical distribution, or Gibbs distribution, right? Gibbs called it grand canonical distribution. Probability to find, you can think of it in two ways. Probability that a system has n particles and in a state J with energy E sub J. You could think of it like that. So it's E minus beta energy of state E sub j, energy of state J is energy of microstate J is E sub J minus mu times n over the normalizing factor, which is called grand canonical partition function or Gibbs sum. Right. Or you could also think of this as what's the probability that a system is in microstate J that's characterized by n sub J particles and energy sub J. Another way, or you could think of this as what's the probability that a system that's able to exchange particles and energy ends up with n particles, and having n particles, it's in the microstate J, the set of microstates dependent n, remember, but it's in a microstate J that's allowed with n particles that has energy characterized by energy sub J. Okay. And then we talked about the Gibbs sum. When you take the second perspective, you can write it as it's a sum over all n of the system, and then sum over all microstates allowable or allowed for each n, and then you would write it like this. You would write it like this. So first, we sum over all possible values of n, and for each value of n, we sum over all microstates, and the weight factor is energy of that microstate. So for each microstate, you drop this type of an exponential factor into the sum. And we used that in the example. And what was the example? The example was you have a bath of an ideal gas, and at the bottom there's basically a substrate with n sites, right? So these are sites. And so you have molecules, you have these gas molecules, and some molecules adsorb onto a substrate. And the question is, what's the average number of occupied molecules given parameters like temperature and chemical potential of the ideal gas and things like that? And I said, well, let's just look at an ensemble of single site substrates, right? So here's one member of the ensemble. Here's another member of the ensemble. Here's a third member of the ensemble, right? And so then we found that the average occupancy, in this case, it could be either 0 or 1. I called it like this. It could be either 0 with probability 0, plus 1 with probability 1. And after a couple of lines of algebra, it was 1 over 1 plus e to the beta e minus mu, but mu of ideal gas is negative. So we can write this as 1 over 1 plus e to the beta e plus the absolute value of mu. And e can be positive or negative. And then when I plotted it, I said for specific values, right? So I think this was for helium at 300 Kelvin. I hope you were able to see what I was writing. I'm sorry. If you were not able to see, here's what I wrote on this page. Here's what I wrote on this page. I'm really sorry. Here's what I wrote on this page. And here is what I wrote on this page. Okay, so let me number pages. Page 2, page 1. Page 3. So for helium at 300 K and basically 1 atmospheric pressure, pressure determines density. So P equals rho KT. And so if we know density, we know temperature, we know the chemical potential. I think chemical potential is approximately equal to minus 0.32 eV. Chemical potential has units of energy, as we discussed last time. And then with these parameters, as a function of energy of the site, a particle adsorbs, that costs energy epsilon. Oh, this is called var epsilon, actually, in Greek, I think. Although I'm sure I'm mispronouncing it. Actually, it's a little bit, sorry, it's not quite like that. So it should be more like, yeah, it should be more like, it should be more like this, right? So it looks something like this. So this is about minus 0.32 eV. This is energy in eV. And by the time it's minus 0.5, it's pretty much close to 1. So this is 1. So that's what this occupancy looks like. I must say, though, that when only one particle can land in a site, occupancy is the same as the probability that a site is occupied. If a site can hold more than one particle, then occupancy is not the same as probability the site is occupied, right? Occupancy could be with, say, 0, 1, 2, or 3 if the carrying capacity of a site is 3. But the probability is always between 0 and 1. But in this particular example, when each site can hold either 0 or 1 particles, occupancy of the site is the same as the probability that a site is occupied, as you can see here explicitly. So it wasn't really necessary for me to invoke the language of occupancy, but it's a good thing to do, because then when we talk about Fermi and Bose systems, then it will be a natural language there. That's part of the reason why I invoked that language. Now, this is an ensemble of one-sided substrates. And so this is really average over what? Average over the ensemble. This is really really the number of members of the ensemble with occupied site divided by total number of ensemble members. But now let's go back to our n-sided substrate, right? It's a substrate with n sites. So this is substrate with n sites, and they're all independent. You see, they're all in the n then. So this is the ensemble, right? It's like bring your own ensemble. So therefore, n is really the number of occupied sites divided by total number of sites. And I use the letter n here, like big N, the total max. And so let's call this little m. Okay, so therefore, number of occupied sites is n over 1 plus e. Let's call it NO, number of occupied sites. I really should still use angle brackets, because this is the average over n-sided substrates. Now imagine an ensemble of n-sided substrates, right? So I have a substrate with 1,000 sites, and then I have another substrate with 1,000 sites, another substrate with 1,000 sites. So this is now average over the ensemble of 1,000 site substrates. But if these angle brackets bother you, then just don't worry about the angle brackets, right? So if it's a sufficiently large substrate, then going from one substrate to another, the fluctuations are going to be small. But technically, it's still an average over the ensemble of n-sided substrates. And then it would be given by this formula. Okay. Okay, so given a substrate with n sites, on average, meaning from one realization to another, and this is how many sites will be occupied, right? This O stands for occupied. Maybe I can use this. Yeah, number of occupied. This is the total number of sites. This is the number of occupied sites. That's good. And I said you could solve this problem. So here we used the trick of thinking about a single site, and then we said, well, all the sites in this n-sided substrate are independent, and so we can think of this as like kind of an ensemble. So if we know the average occupancy per site, then if you multiply that by the number of sites, that gives you the average number of occupied sites, okay? So you got average occupancy per site times the number of sites gives you the average number of sites occupied, average over an ensemble of such n-sided substrates, right? Every calculation that we do in statistical mechanics or in equilibrium statistical mechanics gives you an average in the ensemble sense, right? So this is the usual stuff. Sorry about this bar. This is the holder that holds my cell phone that doubles as a camera. Okay, but now I want to say there's another way of doing this without using this trick of thinking about a single site. So to have that discussion, let's go back to the Z Gibbs sum Z, or grand canonical partition function. It has this structure. Right, this is how you write down the grand canonical partition function. And in doing the calculation that I just did, we had a single site for which n can be 0 or 1. And this sum is also very simple, because if n is 0, energy is 0. And if n is 1, energy is 1. Sorry, energy is epsilon. But in general, you have this. So if I have an n-sided substrate, then n, the number of particles that settle on the substrate or that adsorb to the surface, can be 0, 1, 2, 3, 4, and so on. So then if I wanted to calculate Gibbs sum for this n-sided substrate rather than using the one-site trick, well, it would be a more complicated sum. We'll calculate it in a second. But then what do I do with it, right? How do I extract from such a Z average number of occupied sites? Well, that's like asking, if I have a partition function, the regular partition function, how do I calculate the average energy? And you remember the procedure. The procedure is you take the log, you form free energy, and then you take some derivatives, or you take the derivative of the log of that canonical partition function, and that gives you the average energy. So there's something similar here as well. So therefore, what I'm going to do is I'm going to define the corresponding the function that's similar to the free energy. It's called sometimes it's called grand potential. Sometimes it's called grand canonical potential. Sometimes it's called Landau potential. So grand potential, potential. 1 second, my glasses are bothering me. Or grand canonical potential, or sometimes it's called Landau potential, after the Soviet physicist Lev Landau made huge impacts in condensed matter physics and also in statistical mechanics as well. I'm going to use the letter like script F. Usually textbooks use some other letters. I'm not sure, because every textbook uses a different letter, so I'm just going to invent my own. That would be my notation. And just like the free energy, the definition will be the same. And later we'll talk about other situations, and all of those situations, you can have a volume bath, you can have volume and energy bath, you can have volume and energy and particle bath. All of those have a corresponding partition function and a corresponding function that's called thermodynamic potential. Okay, so as before, we resum the sum so that it's a sum over particles and energies rather than a sum over particles and microstates. Okay, a resum. So Z is a sum over particles, as it already is, and energies. Okay, so how do I turn the sum over microstates for a given n to a sum over energies for a given n? So pause the video and think about it. Okay, the way to do it is to multiply by the degeneracy, because you have multiple microstates with the same energy. And when the dust settles, you know, oftentimes it turns into an integral. So we spent a lot of time very carefully turning that sum into an integral. I'm not going to do that now. I'm just going to write it down. It becomes the sum where delta is the energy bin width, right? So you can define the number of microstates that lie within a shell of energy of width delta, right? Or energy range of width delta. That's where the delta comes in, and you get a entropy. Entropy term, right? Of course, minus beta times minus t is beta t, which is 1 over k Boltzmann. E to the s over k Boltzmann is just multiplicity. Okay, and this refers to system entropy that corresponds to a particular value of n and particular value of energy, and we're summing over all the energies. Okay, so all of something is stuck in my eye. It's really bothering me. All of the E, N, and S are extensive, or they're assumed extensive. And so, as before, for large N, the integral is dominated by one term with some optimal value of E and N called E star and N star. Okay, so dominated integral is dominated by E star and N star. I'll say what they are in a second. And so that the grand canonical partition function is minus beta E star minus mu N star minus T S evaluated at E star and S star. Okay, so what is this? What is this E star and N star? By the way, what I'm saying now goes in parallel to what we did with free energies. So as you're watching this video, you should watch it actively. You should pause it and think. You go back to your notes and see how we got all these results when we talked about canonical partition functions and free energies. Well, E star and N star maximize the exponent, this exponent right here, right? So they maximize this thing right here, right? With respect to energy and the number of particles. In other words, E minus mu N minus T S of E and N equals 0, and partial N E minus mu N minus T S of E N equals 0. And these give respectively 1 minus T partial S system, partial E evaluated E star equals 0, and respectively 1 over T equals partial S system partial So yes, and then also, yeah, so this says that 1 over T, this is the bath temperature. The T that appears here is the bath temperature, equals partial S system partial E evaluated at E star. So E star is the so it's the energy of the system at which its temperature. So what is E star? E star is this is 1 over T of the system. So E star is the energy of the system at which its temperature equals bath temperature. Or in other words, E star is the equilibrium energy of a system that's in contact with the bath at temperature T. Okay, so that's what E star is, right? Equilibrium energy. You have two systems, they come to equilibrium, T system becomes equal to T bath, and when that happens, the energy of the system attains the largest possible, the most likely possible value, not the largest, but the most likely possible value. And then also, you take this derivative, and this gives you what? This gives you minus mu minus T partial S of the system partial N equals 0, evaluated at N star. And so minus mu over T, these are again bath properties. Mu of the bath and T of the bath equals partial S system partial N, evaluated at N star. And these are system properties, mu of the system over T of the system. Okay, and so therefore N star is the equilibrium number of particles in the system that's in contact with the bath at chemical potential mu. Okay, so this N star is the equilibrium N. Okay, so you have that similar situation. Okay, this is page 5. Okay, so I want to make sure that you could view this page. That's what's on page 5. And so now I'm going to switch to page 6. So at equilibrium, we have this usual situation. You have a bath at temperature T and chemical potential mu, and a system that's able to exchange energy and particles. But at equilibrium, if it's a large system, if it's a large system so that you can define its temperature, then its temperature will be equal to the temperature of the bath, and its chemical potential will be equal to the chemical potential of the bath. And if it's a small system, then you can't really define temperature of a small system. Like, what's the temperature of a molecule? It's a mechanical system, basically, a quantum mechanical. Then T in all the formulas really just means the temperature of the bath. But in any case, it reaches some energy N star and some energy E star and N star. And again, if the system is, you see this E star and N star, they're proportional to the number of particles. Let's say E star is proportional to the number of particles in the system. So, and the fluctuations of E, as always, is proportional to root N. So the system is large. Yes, energy can still technically fluctuate, but the fluctuations of the energy are much, much smaller than the mean of the energy. So effectively, the system has essentially a fixed energy. You can talk of the energy of the system as the energy of the system. So what's the energy of the gas? What's the total kinetic energy of the gas in your room? Well, it fluctuates, right? It can exchange energies with walls and with windows, but those fluctuations are essentially negligible. So it's the usual story. Okay, so energy and N are fluctuating quantities, but their standard deviations both scale like root N, so the relative fluctuations scale like 1 over root N. Or put another way, the temperature and chemical potential of the system are given by the results of the isolated system in which energy equals the E star and number of particles equals N star. So effectively, we have an isolated system. It's technically not isolated. It can exchange energy and particles, but the thermodynamic predictions that we're going to make for in this situation where energy and n can exchange with the bath, will match in the thermodynamic limit and the limit of n being very large, will match with predictions of isolated systems that has energy E star and N star. Okay, so all in all, we have this grand canonical free energy, or what did I call it? Landau potential, or grand canonical potential. It's approximately given by E star minus mu N star minus TS at E star N star. But I'm not going to write star anymore because energy and number of particles are acting as if they're just fixed values. And in that situation, so first of all, you can replace the most likely value by the average value. And in a situation when fluctuations are small, I just called that energy value U. So U minus mu N, and then N is just called N, minus TS at U comma N, or U minus mu N minus TS. Okay, so we have the grand canonical potential. It's a function of temperature of the bath, chemical potential of the bath, and the volume. And these are called natural variables for this situation, right? So when you have system that's only open to energy exchange, its number of particles and volume and other quantities. If it's a different system, let's say if it's a magnetic system, volume gets replaced by magnetization, but we've been mostly talking about volume. So those things are fixed. And so the natural variables are temperature of the bath, number of particles, and volume. Now, also number of particles is not fixed. So instead, the natural variables are now the temperature of the bath, chemical potential of the bath, and volume of the system. Volume is fixed. And okay, so how do we proceed? What do we do to learn how to extract thermodynamic variables from derivatives of this? Because that's the usual procedure. So on the one, we do what we always do, right? So on the one hand, 1 second, there's something stuck here and it's really bothering. So on the one hand, we have the total differential of a function of 3 variables, like in calculus, is this plus partial this partial mu d mu plus partial this partial v dv plus dot dot dot. If there are other variables like magnetization, polarization, you would extend this, right? So these 3 variables are not a panacea. You could have other macroscopic variables describing the system. We've been mostly thinking about gas-like systems, but it doesn't have to be just that. So then, on the one hand, on the other hand, we also have so you have a grand canonical potential is U minus mu N minus TS. So therefore, du equals du, sorry, df equals du minus mu dn minus n d mu minus tds minus s dt. Okay, so is du minus mu dn minus n d mu minus t ds minus s dt. And we have this idea that du equals tds minus p dv plus mu dn. This is well, this is called the thermodynamic identity. Thermodynamic identity. Do you remember where it comes from? It comes from a thermodynamic identity for ds. ds equals du over t plus p over t dv minus mu over t dn, and I just multiplied everything by t and rearranged. Where does that identity come from? Well, that comes from our discussion of isolated systems. Okay, so combine So plug into this expression, and then when the dust settles, you would find this equals minus s dt minus mu minus n d mu minus p dv, and compare with, and then you compare with this star. Okay, so if you just compare, so this must be this. So you get S equals minus partial grand potential with respect to temperature at fixed mu and v, and whatever the other variables are. And then this you compare with this. So N equals minus partial F partial mu at fixed temperature and volume. And then you compare this with this. So pressure equals minus partial grand potential partial V at fixed T and mu. Okay, and then you could have other, and you could have other derivatives, right? So let's say if F depended also not on volume, but say electric polarization, then you would have polarization equals minus partial F. You would have electric field equals minus partial of the grand potential with respect to the polarization, something like that. What does this mean? Right, this really refers to the average number of particles. Remember, I said I'm going to drop angle brackets, stars, and everything. But remember, it is n is technically a fluctuating quantity, and this is also a fluctuating quantity. Pressure can fluctuate. Temperature of the system can also fluctuate, right? This T is the T of the bath. Mu is the mu of the bath. V is the volume of the system. So these are technically average quantities, but for a large system, they're essentially fixed. There is also this kind of relationship. I'm not going to derive it, but you can try to see for yourself. This is minus partial beta of log of z. Okay, n is a fluctuating quantity. It's really this really refers to the average n, and this really refers to the average energy, right? This really refers to the average energy. We just agreed that for large systems, we should think of them as essentially just the values rather than fluctuating values. What about entropy? Entropy is not a fluctuating quantity, right? So entropy, remember we had this example with just one harmonic oscillator that's interacting with the bath, and we calculated entropy, right? We plotted the entropy. It was some kind of I forgot, was some kind of a function that looks like this. And I said, well, how can you talk of an entropy of a single oscillator? Single oscillator is a mechanical system. Mechanical system doesn't have an entropy. Well, it's a mechanical system driven basically by a stochastic force, by kicks from the bath. So if we jump ahead to the next lecture and borrow the idea that entropy is a measure of missing information, then you do have missing information when you drive a mechanical system by a stochastic random force. And so this entropy is kind of a measure. This entropy sums over all possible all possible microstates and number of particles in the system. So this entropy basically this entropy knows about everywhere where the system can be in phase space and with what probability. So this entropy is not a fluctuating quantity. Next lecture will really talk about information theory and connection between thermodynamic entropy and information theoretic entropy, and then it would become, then I would come back to this idea, so that this entropy is not a fluctuating quantity, just like things like partition function. It's not a fluctuating quantity. It sums over all microstates. However, you can also think of this for a large system. This is the same as an entropy of an isolated system that has energy star or U and the number of particles given by this value, right? So this is not a fluctuating quantity, but you can also think of this as what entropy of an isolated system would be if it had energy given by the mean energy or E star and the number of particles given by this quantity. Okay. So good. So now we can go back to our example. Back to n sighted. Sure, I want to make sure you could see everything here, right? Yeah, this is the page. So now we're going to go back to the n sighted substrates. And let's substrate, right? So, and let's calculate the Gibbs sum or the grand canonical partition function. So Z is a sum over all possible values of n number of particles that settle on the substrate. It could be nothing settles, one particle settles, or maybe two particles settle, or maybe three particles settle. And then for each n, sum over all possible energies. All possible microstates weighted by energy of each microstate. Now, unfortunately, letter n is already reserved to mean the total number of sites. So I'm going to use letter little n, okay? Little n is the number of occupied sites. I called it NO above, but this is an easier notation. So sorry, I'm kind of switching notations. I can switch back to this at the end, right? But it's easier to write little n than NO. It's just heavy notation. So it can go between 0 and n. We have an n-sited substrate. And so we have the factor beta mu times n, right? That's your e to the minus beta, energy minus mu n, right? So e to the it's this, right? So I'm just using lowercase n. And then this other term is e to the minus beta. So over all microstates, energy of a microstate. Well, let's see. So if you have one particle settle on the substrate, energy is E. If you have two particles, energy is 2E. If you have three particles, energy is 3E. The problem is that you have many microstates with, let's say, 5 particles settle on 1,000 sited substrates. There are many microstates. There are many ways to arrange 5 particles on 1,000 sited substrate. Well, if you think about it, it's just the binomial factor. So I can write this like this. All right. So e to the beta mu n times e to the minus beta n e times this type of factor, right? So let's say you have one particle on a 100 site substrate. There are 100 ways of doing that, and they all cost energy epsilon. What if you have two particles on a 100 site substrate? Well, there is 100 times 99 over 2 ways of doing that. Why 2? Why over 2? Let's go back to coins. Coins are easier to visualize, right? So you have a bag with 100 coins. and you pull out 2 coins. Now each coin is labeled. Each site is labeled. The particles are indistinguishable, but the sites are distinguishable. So you can label site 1, site 2, site 3, just like you can label coins. So one combination is coin number 1 and coin number 7. Okay, and you can pull out coin 1 and 7 in 2 ways. First coin 1, then coin 7, or first coin 7, then coin 1. And usually we don't care. It's just one combination is coin 1 and coin 7. Another combination is coin 1 and coin 5. Another combination is coin 3 and coin 25. Okay, we don't care about the order in which we pull those coins. So that's why we divide by 2. Or in other words, that's why there's this factor right here. Okay. Anyway, it's a binomial. It's just a familiar binomial situation. So you can write that as n equals between 0 and n of n factorial over little n factorial, n minus little n factorial x to the n, where x is e to the beta. I'm going to do this. I'm going to bring in the minus sign inside. It's just kind of easier. Well, it's basically what I wrote, right? And you know what this. Okay, so I want to make sure that you're able to see this. And you know what the answer is, right? So the answer is, after you sum that sum, it's 1 plus e to the beta minus e plus n, plus mu, sorry, all to the power n, okay? And now I'm going to use the formula that we just derived. It was minus partial f partial mu. Now f is minus kt log of the grand canonical partition function, which is minus kt. When you take the log, you bring the n times the log of 1 plus e to the beta minus epsilon plus mu, like this. And so now I'm gonna do this, which is partial, well, I'm just going to take the derivative, and that minus times minus gives a plus, and I take the derivative, it becomes ktn 1 plus e to the beta minus e plus mu. I take the derivative with respect to mu, I bring the beta down, that cancels the kt in a moment. The beta minus e plus mu, that's n 1 plus e to the minus beta minus e plus mu, and that's just n over 1 plus e to the beta e minus mu, but mu is negative. That's the same as n over 1 plus e to the beta e plus the absolute value of mu. So same result. And I can just call it the number of occupied sites, okay? That's what I really mean by little n. So you get the same result. Okay, so we could use this mental gymnastics of thinking about a single site and then realize that, well, if we know the average occupancy of the site, that's the same as this average over the ensemble is really the same as average of this over the system. You can think of the system as the ensemble. So therefore, average number of occupied sites is the average occupancy per site times n. We could do that, or we could just turn the crank. We could just use the machinery. You have the n site substrate. You calculate the grand canonical partition function for it. The T and the mu are the temperature and the chemical potential of the bath, which is the gas above it. And then you calculate your grand canonical partition function. You take all the logs you need to calculate the grand canonical potential, and then you take the derivative, and boom, you get the answer. Okay, all right. So I promised 2 examples. Okay, so now that we have the machinery, let's apply it to the ideal gas, right? So let's apply it to the ideal gas. So example two, ideal gas in contact with the energy and particle bath. Okay, so the ideal gas in contact with the energy and particle bath. We discussed you can write down the grand canonical partition function like this. So you sum over n, z to the n times this is the lowercase z, sorry, this is not the partition function. This is the n particle partition function. The n particle partition function, so what's the partition function of the ideal gas with n particles in it? Well, we know the answer. This is 1 over n times v over v quantum raised to the n power, okay? What is the little z? Little z is e to the beta mu. I'm sorry that the script z is already taken. Sorry, this is supposed to be to the power n, okay? So the grand canonical partition function with the ideal gas is 1 over n factorial z times v over v quantum raised to the power n. Oh, this is just the Taylor expansion for the exponent, for the exponential, e to the zv over v quantum. Okay, so I hope you understand. This is just the Taylor expansion for e to, this is like e to the x equals 1 plus x squared over 2 factorial plus da 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 da. Okay. Oh, so this is the same as e to the z times regular partition function for one particle. Okay, grand canonical potential is minus kt log of z, which is minus kt times z over z1, or minus f over kt equals z over z1. We will come back to it in a second. Or you could also write it like this. You could say the grand canonical partition function, the grand canonical potential, the equivalent of the free energy, or the grand canonical free energy, is minus kt equals to the beta mu times v over v quantum. Okay. Okay. Now we're going to take our derivatives. Okay, so we derived the Landau potential, the grand canonical potential, and now we're just going to turn the crank, right? So the first thing that we can do is we can calculate average number of particles inside the system. It's minus partial f partial mu. When the dust settles, after a couple of lines of algebra, you get e to the beta mu times v over v quantum. So okay, so then you can invert it, invert, and then when you invert, you get mu equals kt log of n vq over v quantum. Oh, oops, vq over v. Or that's the same as kt log of rho over rho quantum. Rho is typically is going to be much smaller. In order for this formula to work, remember density has to be much smaller than quantum density, so we get a negative mu. And this, by the way, is how I discovered, I got this result, and then I compared with before. I said, wait a second, before we didn't have an n, and I realized that I just made a mistake on the previous lecture. Okay, so, okay, good, this is good, but in this case, mu is fixed by the bath, and it's really that this is, so this is really the meaningful formula now, right? Because it gives you the average number of particles. So here's your ideal gas, and it's interacting with a bath. The bath could be some other. Bath could be anything, actually. Well, the bath has to also store particles, right? So if it's a kind of bath that's able to provide or take particles from the ideal gas, it cannot be like a bath of spins, right? Because spins don't contain ideal gas particles. So it's probably just a bigger ideal gas system. Okay, and so it gives you really, remember what this means. This is really just the average number of particles in the system. But again, if system is very large, fluctuations of n very negligible in comparison to this average, so we can just treat it like the number of particles. Okay, what's the next thing we can calculate? We can calculate pressure. So we can do this. Well, make sure you could see what I wrote here, right? The next thing we can do is we can calculate pressure. We can take this derivative, so we can do this. P equals minus partial F partial V. You might ask, do you have to remember all these derivatives? First of all, no, you have your formula sheet. And second, no, you don't have to remember them. You have to know where they come from. Okay, we've done this procedure at least twice by now. So when you do the derivative, you get kt e to the beta mu over v quantum. I'm going to multiply by and divide by v. So this is kt over v e to the beta mu v over v quantum. And what is this? This is just what we found for number of particles, the average number of particles, right? So e to the beta mu v over v quantum. So this is really, I'm just going to write n. Although remember, really it's the average n, right? It's the average number of particles, right? So, well, that's it. So we get PV equals nkt. Or really, what we predicted is the average pressure times volume equals average number of particles times kt. Whereas the canonical versus average pressure times volume equals fixed number of particles times kt in canonical calculation. Right, so even though this looks identical, remember that in this particular calculation, P refers to the average pressure and N refers to the average number of particles, whereas in the canonical calculation, N is fixed. So these have slightly different meaning. A good question is what's the reason that the expressions for averages have the same structure? Okay, so it's a good question. I'm not going to address it right now. And then the third thing we could do is we could do this u minus mu n equals minus partial z log of partial beta log of z, which is the same as partial beta of beta times the grand canonical potential. I'm going to skip algebra. Okay, so I'm going to skip algebra. You have to use this idea that 1 over v quantum equals 2 pi m to the power 3/2 over h cubed times beta to the power minus 3/2. Okay, so you have to, in taking, because we're going to take the derivative with respect to beta, right? So beta is stored inside v quantum, because remember your f is minus kt to the beta mu v over v quantum. So beta f is well, it's minus e to the beta mu v over v quantum, right? So that's what beta f is, and v quantum depends on beta. So it's got a little bit of lines of algebra, but at the end of the day, you would get u minus mu n equals 3/2 n kt minus mu n. And then you compare that u equals 3/2 n kt. Okay, so again, it looks like the same as what we had before, although before n was fixed. Now n refers to the average number of particles. So it gives you the average energy equals 3/2 times the average number of particles times kt. Or you could say both expressions say that the average energy per particle is 3/2 kt. And that's a fixed number in both calculations. So sorry, I have to skip steps, but it's just basically just straightforward, just taking lots of derivatives. Yeah, it's just taking derivatives there really is nothing to it. And using and using, for example, when you take derivatives to get this, you would have to make use of this result. Yeah, and then you would just end up with this. Okay, so let's see. So this is page number 11, I believe. Page number 11. There's one other interesting thing here, page number 12. So there's one other interesting observation worth noting in connection to this. Note that P times V equals KT e to the beta mu V over V quantum. Okay. But also, the grand canonical potential equals minus KT e to the beta mu V over V quantum. So evidently, the grand canonical potential is minus P times V. Oh, interesting. Why is that? Why is that? So this is a special case of something called Euler relation. We won't really dwell on this, but since we ran into it, I would like to address it. So we have this type of thing. The thermodynamic identity for this particular brand of system interacting with the bath. Let's say I take a bunch of small systems all in contact with the same bath at a given T and mu, and I bring them together to build a larger system, right? So so you have a bunch of small systems. This is a bath at a given T and mu. So you have system 1, system 2, and system 3, and I bring them all together to construct a bigger system at the same T and mu. Okay. Now, so what I really have is I have F big equals sum of F small, right? Right? So you could say that this is the sum of df, right? At fixed t and mu. So in this case, dt is 0 and dmu is 0. So this is really minus p dv. If they're all at the same t and mu, they will all have the same pressure. So this is minus p times v. So this is an interesting idea that if you have a system that has some intensive variables, right? The bath is always characterized by intensive variables. Temperature, chemical potential, pressure, these are all intensive variables. You can think of building that big system by combining a bunch of smaller subsystems in contact with the same bath, characterized by the same intensive variables. And then you can use the appropriate thermodynamic identity to realize that your thermodynamic potential, free energy or grand canonical potential or something else, enthalpy, Gibbs free energy, can be expressed. There's some other way of expressing this in terms of thermodynamic variables. So on the one hand, we have this is given by, you remember that what is it? I forgot. So it's given by E minus mu n minus Ts. That's true. But on the other hand, it can also be expressed like that. In any case, I just wanted to say that in passing. We're not gonna spend time studying this, but it's just an interesting observation that, whoops, interesting. Like, where does this come about? Well, evidently you can explain it like this. And so if we knew that from the very beginning, by the way, if we knew that from the very, very beginning, then we could go back. We could just realize that F over KT is really PV over KT, and that's equal to fugacity times regular partition function of one particle, and then we could basically calculate fugacity, and we would find that n equals fugacity times the one particle. What I'm trying to say is that we could, if we knew that from the very beginning, then we could make use of it earlier, right? So we could, for example, this becomes minus PV over minus times minus PV over KT. So this PV over KT, and what is this? Well, this is just n, right? It turns out that this is just n, because this is your one particle partition function. You see, this is your z, and this is your z1. And so you get PV over KT equals n, PV equals nKT. Yeah. Anyway, knowing these types of relationships is knowing these types of relationships is sometimes helpful, but it's okay. We didn't need it. We could just turn the crank. All right. So this is what I think I'm about 1 hour in. So I'm going to stop the video, and I'm going to record a separate video for the second hour, and basically done with what I wanted to say about grand canonical ensembles, grand canonical partition functions, grand canonical potentials. What do I want to do next? I want to, before moving on, I want to step back. And now we've seen several types of physical situations, right? We've talked about an isolated system, then we've talked about a system interacting with an energy bath, and we talked about system interacting with a particle bath. And you start seeing patterns. All of these things have partition functions, except for isolated systems. All of these systems have some generalized thermodynamic potential. So in the first case, it was Helmholtz free energy. In the second case, it's this Landau potential or grand canonical potential. And we could imagine other baths. We could imagine a volume bath. We could imagine a volume and particle bath. We could imagine a volume and energy bath. We could imagine a volume and energy and particle bath, all sorts of things. And they all would follow in parallel track. So I want to have a little discussion about these generalized situations and have a little discussion of these things called thermodynamic potentials. So we'll do that in the second hour. And after we're done with that, I would like to, since we're on the subject of thermodynamics, I would like to have a discussion about heat work and the second law. So this is the very thermodynamic type of discussion. It's not. It's usually it's like a heart of thermodynamics. The discussion of Carnot cycle comes with it, and I think it's important to have that discussion so that if you ever run into it in the future, you could look at your notes and consult your notes. After that, I would like to talk about connection between entropy and information theory. And that will give you a different light of looking at things. And that would be the end of the second part of the course. And then we will move on to the third part of the course, quantum, quantum gases, basically. Fermi gas, Bose gas. And we are kind of behind. That's okay. So I would have to think about how to shorten that topic. And well, that's okay. It's my first time teaching the course. It's not going to go perfectly, but let's just get as far as the guest takes us. Okay, so I'll see you in the second hour and we'll talk about thermodynamic potentials. Thank you.